Hello there, my partner Raimundo José Muñoz Pons and me, Ángel de Alcántara González, are going to talk about this article, Genetic Programming with Image-Related Operators and a Flexible Program Structure for Feature Learning in Image Classification. Talk about the problem description. As we know, image classification aims to assign each image in the dataset with a predefined class label based on the content in the image. To do this correctly, the feature extraction is critical, where low-level pixels values are transformed into high-level features. However, feature extraction is challenging because of the high interclass and intraclass variation across image. Also, because of the traditional methods need expert knowledge and are limited in flexibility. The variability in the scale, rotation, lining, and background in the image can affect, as we said before. The neural network, such as CNNs, require high computational resources and extensive data. As we all know, the programming is an evolutionary computation technique and can automatically evolve computers programs to solve problems using the principles of biological evolution and natural selection. Genetic programming has been applied to image feature learning and achieved promising results. The objective of the study is to develop a new GP-based approach with image-related operators and a flexible program structure to feature learning for different image classification tasks. The authors wanted to create a flexible structure that allows the learning process to adaptively generate suitable features for different classification tasks, from simple to highly complex scenarios.
Now I'm gonna talk about the proposed algorithm called FGP, Flexible Genetic Algorithm. Well, this algorithm is very similar in structure to the genetic programming algorithm, and with the difference that in this algorithm integrate multiple layers for filtering, polling, and feature extraction to improve adaptability and representation power. The structure is the following. Well, the difference between this algorithm and the genetic programming is here we use a cache table to avoid re-evaluate the fitness value of individuals that the algorithm have evaluated before. And the second difference is how it generates the population for the next generation. Here in this algorithm, the next population is generated by taking two samples. One sample is going to be a group of the best individuals using LTS operator from the previously population, and the second sample is going to be individuals selected from the previously population using the tournament selection. Once you have this second sample, the algorithm generate a offspring using the second sample through using tree crossover and tree mutation operators. And then the fitness is evaluated for each individual of the offspring, and the next and the population for the next generation is the combination between the offspring and the best individual of the previously population. The way that the fitness is evaluated it's with the next algorithm. First, if the individual is now in the cache table, we're gonna train a linear SVM model using the features that the program or model that it's gonna recover from the image, or the features that are gonna the vector features that it's gonna generate the individual. And the fitness value it's going to be the average test accuracy of the k-folds. These are the functions that are going to be nodes of the tree. We have three kind of functions: filtering and pooling functions, feature extraction functions, and concatenation functions. The concatenation functions are going to be always the root, or are going to be always in the top level of the tree, because these functions it's going to make sure that the model or program are going to return always only one vector, that it's going to be the vector with the features. Finally, we have the terminals. The terminals are going to be, in short words, are going to be always an image with random constants that are required for the previously functions. For example, the standard deviation is used by the Gaussian filter, and it's randomly initialized in the range of 1 to 3, and the same by with the other constants in his own range. And these are the examples of some programs and models that the new approach are gonna generate. And as we can see, always the model are gonna generate a output that it's gonna be a vector of futures. And now I'm gonna leave you with my companion Angel Jael. He's gonna talk about the results of the experiments.
Well, now let's talk about the results. They evaluated this technique on 12 datasets. Well, for the facial recognition on these datasets, the accuracy ranged from 92% to 95%, significantly outperforming baseline models. This GP-based approach achieved higher accuracy compared to traditional methods, effectively handling variations in facial expressions and pose. For the texture classification using this dataset, the algorithm excelled in recognizing textures under different scales and lighting conditions. It got an accuracy of 94%, which was 5 or 10% higher compared to other feature extraction techniques. For the digit recognition with these datasets, the algorithm achieved accuracy on these datasets range from 90% to 96%, demonstrating robustness under challenging conditions. Particularly on the MNIST variant datasets, this approach showed superior adaptability in the scenarios involving rotated digits, random backgrounds, and varying levels of noise. And for the object classification, the method demonstrated excellent performance on binary and multi-class object classification tasks. It provided a more flexible representation compared to fixed neural network architectures, with accuracies of 93% to 97%. Now let's talk about some key advantage. The first one is no need for domain-specific knowledge. The features are automatically generated, reducing the reliance on manual feature engineering. The interpretability, because of the evolver solution, are represented as trees, making them easier to interpret compared to deep neural networks. And the adaptation to stacks complexity, because the flexibility of the tree-based structure allow the solutions to adjust their complexity based on the difficulty of the tasks. Now the conclusion is that the approach, this method outperforms several traditional and CNN-based methods across multiple image classification tasks. It demonstrated that the effectiveness is very good in diverse scenarios. For future work, maybe we can investigate a little bit for the scalability, how the approach can be scaled to larger datasets, such as as ImageNet, to validate its effectiveness in big data scenarios. And for optimization, we can focus on optimizing computational performance, possibly through parallel processing or more efficient genetic operations. And well, that's all. Thank you for your attention.